students, and welcome to today's lesson. I'm Mrs. Levine. Today, we will investigate the question, how can we use patterns to predict motion? Are you ready? Grab your pencil and your science journal and let's get started. Whoa, look at all these toys. As I show you this video clip, I want you to focus on the motion of this marble. Ready? Wow, that video clip was short. What do you notice about the marble? I noticed that the student drops the marble into the top of a funnel. Let's play the video clip again. Okay, so the marble is here now. I wonder what will happen if the marble continues rolling. What do you predict will happen? Let's continue watching the video clip to find out. Let's watch one more time. Did you see that? The marble rolled down the track and hit the first domino. Each domino then hit the domino next to it. One of the dominoes then hit the tower, which hit the car. The car rolled into the other dominoes, which fell and hit the bell. Did you predict the objects would hit each other until the last object hit the bell? Great! How were you able to make a prediction about what would happen? Maybe you've played with dominoes before, so you know that when you line dominoes up and then push one over, the dominoes fall into one another. Did anything else help you make a prediction? Oh yeah, we observed the motion of balls and cars at the motion stations. At the ball station, we watched balls bounce, but I know that balls can roll. So I predicted the marble would roll like a ball. We were able to make predictions about the motion in the video clip because we have seen the motion of other objects. The more motion we observe, the better we get at predicting motion. Let's revisit the pendulum station. Guess what? I have a new pendulum for us today. This pendulum uses a film canister filled with pennies at the end instead of a washer. However, the film canister pennies and string still form a pendulum. Do you think this pendulum will move the same way that the other pendulum did? Let's find out. How can you describe the film canister pendulum's motion? Does its motion fit the patterns we described for the pendulum at the pendulum station? The new pendulum also swings back and forth. So yes, it fits the patterns we described. Now I've got a challenge for you. In this challenge, we'll use the new pendulum and the toy car. When the pendulum and the toy car interact with each other, they make up a system. The pendulum is one component of the system and the car is another. To make the components of our system interact, we will swing the pendulum so that it hits the car. When the pendulum hits the car will roll forward. Suppose we want the pendulum to swing and hit the car so that the car rolls to a specific spot. Do you think the pendulum and the car will have mechanical energy? Yes, the pendulum will have mechanical energy when it is swinging. The car will have mechanical energy when it rolls across the floor to the specific spot. What might be challenging about setting up the components of the system? We would need to put every component in exactly the right place. I think doing that would be challenging. Also, if one of the components didn't work correctly, then the whole system wouldn't work. Predicting the exact motion of an object may be challenging. We could use observations of patterns we saw with other objects to make general predictions, but sometimes people need to make predictions that are very close to the actual results. Let's keep exploring the question, how can we use patterns to predict motion, to figure out how we can predict motion more precisely? Let's start with an investigation. Let's see. How far will the toy car move when the pendulum hits it? What do you wonder? I wonder if the distance the car travels depends on how hard the pendulum hits the car. What do you think will happen if we release the pendulum multiple times from a different height each time? What do you wonder? I wonder, will the car travel different distances each time? How can we interact with the pendulum and the toy car to make sure we answer our question consistently? We should make sure that our investigation is a fair test. In a fair test, we change only one condition at a time and keep all other conditions the same. What questions should we ask for our investigation? Well, we want to release our pendulum from different heights, right? And we want to see how that release distance affects the motion of the toy car. Let's ask, how does the release distance of the pendulum affect the distance the toy car travels? This question is a testable question because it can be answered by using evidence gathered through investigation. We'll use this testable question to design a fair test investigation where we will change one variable at a time. But what are variables? A variable is any condition or factor in an investigation that can change. Only one variable in the investigation is changed by an investigator at a time. For our investigation, the only variable we will change is the release distance of the pendulum. Let's add this information in the second column of our fair test guidelines chart. Here's how we have set up our investigation so far. The only variable we will change is the release distance of the pendulum. So what other variables will we want to keep the same? Maybe you said we need to make sure the length of the string on the pendulum is the same every time. And we should use the same number of pennies in the film canister every time we release the pendulum. We should put the toy car in the same place each time we release the pendulum. Oh yeah, we should make sure the string is not loose. The tightness of the string should be the same for every trial. We have filled in a lot of the chart, but we need to make sure we gather our data in the same way each time. How can we make sure that we gather data consistently? What do you think we should do? Of course, we should take measurements to describe the distance of the pendulum and toy car. I wonder, is there anything else we can do to gather data in the same way each time? We should also record our data in a table. Wow, look at our fair test guidelines chart. We are almost done. But how can we make sure to gather data as accurately as possible? What do you think we should do? Maybe you said we should use a metric ruler to measure the distance the pendulum bob is pulled back. Let's use centimeters. Great. Can you think of anything else we should do to gather data accurately? Yes. We should also use a meter stick to measure the distance the toy car travels. Remember, we will take our measurements in centimeters. Wow, we did it! We've planned our fair test investigation. Great work! Our investigation can help us predict the motion of an object, the toy car. Why do you think predictions about the motion of objects might be important? Imagine you are at an airport and a pilot is about to land an airplane. Why does the pilot need to be able to predict the airplane's motion? I wonder what will happen if the pilot doesn't predict the correct motion. If a pilot doesn't predict the motion correctly, the plane might run off the runway. Think about our book, Moonshot, The Flight of Apollo 11. Why were predictions about motion important for the moon landing? For your first task today, you will answer this question in your science journal. We had so much fun planning our investigation today. How can the investigation we planned help us predict the toy car's motion? For your second task, you'll answer this question in your science journal. In the next lesson, we'll conduct our investigation to gather evidence that will help us predict the toy car's motion. Let's review your task for today. First, answer the question about the moon landing. Second, answer the question about the investigation.